substation hierarchical control is exact same as that of the asset condition monitoring, as you can see on your screen. Next slide, please. Here are some of the glimpses of KCP&L human machine interface. Next slide, please. Expected versus actual result. Substation hierarchical control will pave the way for great learning and experience for industry. Moreover, it would provide the remote monitoring and operation of all substation from single point. This would increase the level of safety for operator. With this, I would like to hand over this presentation to my colleague Priya.
Thank you, Nikhil. My name is Priya. Now I am going to discuss about real-time load measurement and management. It provides about real-time load measurement of customer consumption and management of load through AMI systems that help customers make informed energy. First, we need to know difference between AMI and AMR. AMI is nothing but AMR is nothing but it creates a connection between a business customer and its energy supplier, and it goes in one direction. Whereas AMI is a collective term to describe the infrastructure from smart meter to two-way communication network. Next slide. Hello. This provides an overview of the operational demonstration and testing and evolution. Now we'll go through the description. Here, AMI was deployed into the entire KCP&L smart grid demonstration area, around approximately 14,000 residential, commercial, and industrial customers. It will transmit 15 minute interval energy usage data to the central MDM system. Next, communications between meters and the MDM was through dedicated RF message field area network and wide area network. Next slide. The operational demonstration of the AMI was expected to yield the following. AMI would capture meter reading at 15-minute interval as opposed by the AMR system. AMI would provide the interval metering and communication infrastructure required for the many of the SGDP, that is Smart Grid Demonstration Project applications. Here the benefit analysis method. These are the benefits were quantified. Reduced meter reading cost and reduced electricity theft and reduced CO2 emissions. Next slide. These are the testing for the application, and these are AMI interval metering was deployed in the late 2010 to replace legacy AMR meters for all the customers within the SGDP area. And it was captured by AMI meter reading was captured by the AHE, that is AMI head end system, and AMI daily read performance was captured by the legacy CAS system, that is customer information system, and AMI meter reads were processed by the AMM head end and sent to the meter data management, that is MDM, and data mining and analytical tool for building, processing, analysis, reporting. Next, these are the analytical methods that we need to evaluate the impact of the benefits of this application. They are load data for the customers within the project area and from the MDM. And DMT was to calculate the 15-minute interval hour to hourly interval data. And these were extracted from the AHA and CAS system. Next slide. These are the planned executor analysis. Here the test were performed, data was collected and analysis were done here. That is daily meter read performance. This was here the table shows that AMI meter performance meters have been reported and shows that over the course of SGDP, and we observe that the AMI network has a 99% from the last year, that is 2013. Next slide. Okay. AMR system covering 5 lakhs meters in metropolitan Kanha city. One of this objective of this operational test was to determine that AMI system would provide improved meter reading performance over the legacy AMR system. The daily performance stats were present in the figure. Here it is showing that AMI system provide more consistent performance than AMR system. AMR reads over 99%, whereas AMR showing somewhat less than, that is 2% less than AMI system. But AMI system is decreasing in August and September months. So they started to replace with this AMR. So they have seen that increase in the performance. Next slide. Meter interval usage data completeness. This project team analyzed that the AMI interval data collected by the MDM over the last year of the demonstration system. This table shows that the AMI interval data matrix calculated and shows that 99.96% of the interval data was collected, whereas 99.98% of meters has complete data, whereas 0.09% are the incomplete data. Hours usage profile by rate class. Here DM80 to aggregate the 15-minute interval to hourly interval data aggregated by the customer class. Here the figure shows the final meter data reported for the smart grid residential rate and commercial rate classes. Next slide. Smart meters and AMI infrastructure devices can be programmed to vast number of event notifications like alerts and alarms. Generally, this event notification can be classified in one or more. Some of these events may be analyzed by addressing by AMI infrastructure, but majority of them were passed to the MDM system. The following table provides the actual outcome for the automatic meter reading operational demonstration. AMI captured 15-minute interval usage data from all meters and improved the daily meter read success rate over the legacy AMR system. AMI supported numerous project reporting and analysis requirements and provide the communication infrastructure for most of the smart and use components and functions. Next slide. Now let's summarize this total. AMR system was aging and failures were increasing, so they started to use this AMI system. AMI system can save money for electrical utilities, whereas it provide data 15 minutes instead of once a day. AMR meters have support time of use pricing. They enable remote connects and disconnects that dramatically improve power outage and power restoration. And we can see the 99% AMR meters were providing. We would we are lucky that 25% of the outage is reported. Now we are seeing 90% of the outage is coming in and more than 95% of the restoration messages are getting, so we can easily can be calculated due to this improvement. Next slide. Due to this improvement, 3169 truck rolls were avoided during the testing period. Next slide. Now we will see about customer uh, sorry customer electricity use optimization. Here customers are provided with information to make educated decision about their electricity use. Historical interval usage information is one accept for the customer electricity use optimization function. Same as it is like overview will done with operational demonstration, testing and evaluation. Next slide. All customers in the SGGTP were provided access the KCP&L Home Energy Management Portal website to present customers with various tools which may visualize and analyze the detailed energy usage history. That is done by My Smart Portal. The HEMP, that is Home Energy Management Portal website, was accessible through KCP&L account link website and provides customer with, that is historical usage information in 15 minutes intervals generated from the customer smart energy and presented with user-friendly visualizations. And we can also provide bill data information with day to day, and also some information tools, advice and program to manage the reduced electricity costs. Expected results are we can expect that this would provide an historical interval meter data available on the heap to better understand the total energy consumption and patterns. Customers would find the bill to date and estimate bill information provided on that website. Next slide. These are the benefits that we get from this website, that are reduced electricity cost and reduced total residual electricity cost. Testing methodology includes that 15 minutes interval load data was collected from the website participants throughout the project period, and 15 minutes interval load data was collected from the heap control group throughout the project period and outside the project area also. Next slide. These are the analytical methodology. The following points provide an overview of the analytical methods. That is 15 minutes interval load data from the control group of the heap participants were extracted from the KCPL DMT for analysis. Load profiles of heap participants were compared with those of select control group customers for hourly, daily, and monthly. Plan execution and analysis. This provides the test performed, data collected, and analysis were performed. Next slide. The main functions of the heap was to ability for the customer to view information about their energy usage, and it also estimate billing information to the customer. Next slide. Program participation. Customers with a smart grid of AMI were eligible to create an account in the heap, and they found that at the peak of the program there were 2,109 customers with the portal accounts, which were shown in the figure, and they are tracking the total number of customers who created an account on the portal, and also they also wanted to gain insight about the behaviors of these account holders over time. So Google Analytics was used to track portal usage over time in order to get better understand how customers were using the portal over time. And they found that 49% of the first portal version sections were from the repeat users and 57% from the second version from the repeat users. And also they plotted the trend lines to show the percentage of repeat monthly users increased over time for both versions. Additionally, they found that the second trend line was increasing at a faster rate. Next slide. Next slide. Customer experience. During the spring 2014, they found that 53% to reduce electricity usage and 45% to take steps to save energy in their home over the previous 12 months. They found that 71 respondents began to the survey and 49 respondents completed the survey. So they have conducted an online survey on that. And actual outcomes, we got that after using this my smart portal, they understood that the types of action they need to take the reduce electricity usage and save money, and bill to date and estimated bill information were both shown in the home page. And according to the survey result, they found that 64% of respondents thought that this page was very useful. Next slide. Lastly, we'll summarize this. They provided a significant insight about deploying a customer home energy management portal. It is clear that customers signed for HEAP accounts to help understand and control their energy use. Based on this analytics, enrollment, and usage data, it is clearly continued marketing to HEAP users. It is necessary to encourage portal usage information over time. Lastly, although customer expressed a desire to save money and energy. Now, Rishabh will continue furthermore.
Thank you, Priya. Good afternoon, everybody. My name is Rishabh Kimpala, and I'm going to take over from here, dealing with storing electricity for later usage. As we know, remote control of electric. One second. Yeah. Yes. Am I audible?
Yes, you're audible. Go ahead.
Yes. Yes, sir. Remote control of electricity storage, which is inflow and outflow, reduces energy costs and enhances the power generation and transmission and distribution capacity utilization. Now we are going to see why and how it is done. Yes, coming to the electric energy time shift. What is electric energy time shift? It is an application which involves storing the electricity when the price of the electricity is low and discharging that electricity when the price of the electricity is high. The energy that is discharged from the electric storage could be sold to the wholesale market, sold under the terms of power purchase agreement used by an integrated utility to reduce the overall cost providing by the generation during the peak times. This is a battery inverter interconnection between the grid and the battery. Here we have advanced metering infrastructure, which has been explained by Priya just now. Here and this is the storage management system. And here the storage management system lowers the charging current to protect the battery from overcharging. The circled areas here shows how the storage management system reduces the charging rate if the battery approaches the full full charge state and then trickle charging at the end of the charging cycle. This is the net battery and the circuit load profile shows the net impact in the circuit for battery energy storage system daily charge and discharge cycle. Coming to the followed by the next reason, which is electric supply capacity. As the demand on the electric grids grow from year to year, the need to install additional generation capacity to meet the demand also grows. The electric supply capacity application involves using the energy storage rather than additional generating capacities, generations. We use the energy storage to reduce the need to invest in new generating capacities. What are the benefits? These are the benefits. Primary benefits are we use the optimized generation operation, deferred generation capacity investments, deferred transmission investments, deferred distribution investments, and to the society we reduce the CO2 emission, SO2 emission, NO2 emission, and PM emission. Testing and I'm so sorry. Methodology. Energy delivered to and received by the battery energy storage system was measured on a high side of the battery energy BESS interconnection transformer through EMI system deployed as part of the project. Energy delivered to the received to power conditioning system and battery was measured in SMS, HMI utility, the PCS and CTs and PTs. All the data collected were stored in SMS and HMI. Multiple charged events were connected to evaluate the potential maximum discharge level that were sustained for 1, 2, 3, and 4 hours discharge event. Now, coming to the planning, how it is planned and analyzed. The following section provide the detail regarding the function test performed, the data collected, and analysis performed for electric supply capacity operation test. First is the potential system peak load reduction. Here, we perform an analysis to identify the potential system peak load reduction that might be realistically achieved with the battery energy storage system. Here, it is shown the hourly annual load profile of KCP&L system for the year 2012, during which a peak load of 3,642 megawatts was achieved. And coming to the 2013, a similar load profile was produced, but a maximum load of 3,382 megawatts was registered. This shows the minimum and maximum load for 2012 and provides a better visualization of daily and seasonal load function. So what do we learn from this? What are the results through the operation and analysis of BESS for electricity supply function? The manufacturer's recommendation that the battery should not routinely discharge below 20% charge level to protect the battery and maintain its life must be factored in which sizing the battery storage component for any battery energy storage system. For battery energy storage system, resources operated for electricity supply capacity, the optimal economic configuration of BESS assets is to install between 2.5 megawatt hour and 5 megawatt hour of storage capacity for each megawatt of inverter capacity. Coming to the followed by next reason, which is transmission and distribution deferral. Transmission and distribution upgrade deferral application involves installing energy storage in order to delay transmission and distribution system upgrades. The transmission capital investment must maintain an extremely high reliability of the electric delivery system. Therefore, an energy storage solution that defers the need for transmission and distribution investment must similarly maintain the reliability of the system. Here we learn that the transmission and distribution has numerous considerations which we realized and should be noted for the implementations. So we learn from here is that The ability of BES to defer transmission and distribution capacity investments is very site specific and will vary greatly based on the load profile at the point of the congestion. This analysis shows that a BES alone may produce a 5% reduction in distribution transformer and circuit peak loading. Based on the demonstration analysis, it appears that BES optimally sized for transmission and distribution upgrade deferral would have 0.5 to 2 megawatt in inverter paired with 4 to 5 times to inverter rating in megawatt hour battery storage. Coming to the followed by again time of usage, energy cost management. This is the other reason for now the time of usage, energy cost management application, energy and users could use a premise energy storage battery system to reduce the overall cost of the electricity. That would accomplished by charging the storage during off-peak periods when the electric energy price is low. Then the discharge energy during the then we discharge the energy during the times when the peak time of use energy prices apply. The application is similar to electric energy. Application is similar to electric energy, that time shift application, although electric energy saves are based on the customer's retail tariff, whereas the benefit of the electric energy time shift is based on the prevailing wholesale price. Here we learn that differential in tau rate need to be at least 16% for the customer to receive and monetary saving. The best demonstrated that has considerable flexibility in how it can be applied to the provide a maximum customer benefits, but it must be tailored to specific customer load profile and rate structure. Coming to the renewable energy time shift. The renewable energy time shift application involves storing the electricity from renewable sources where the prices of the electricity is low and using that stored energy when the price of electricity is high. Because solar typically produces its maximum energy midday when electricity prices are typically lower, the prices differential between the electricity used to charge the battery and the electricity sold at the peak can be significant. These are the best installation of the smart grid demonstration house. Yes. Here we learn that the manufacturer recommendation that the battery should not be routinely charged above 95% and discharged below 10% charge level to protect the battery and maintain its useful life. Differential in tau rates needs to be at least 16%, which we have already covered. And yes, BES could achieve greater savings from renewable energy time shift for the customer with one round tau rates. The best benefit could be further maximized when operation in conjunction with time of use energy cost management function in conjunction with year-round 3-tier tau rates. The best demonstration, it has considerable flexibility in how it can be applied to provide maximum customer benefits, but it may be tailored to specific customer load profile and rate structure. Now my friend Nikhil Naidu is going to take over from here.
Okay, coming to metrics and benefits reporting, the SGDP operational demonstration and testings outlined previously were performed to not only demonstrate the smart grid functions achievable through end-to-end interoperability, but to also capture and quantify the operational benefits achievable by each of the smart grid application. The EPRI and the DOE have developed specific quantifiable methodologies to translate benefit metrics into potential monetary value. The KCP&L used the DOE developed metrics reporting and computational tools to evaluate the overall cost and benefits of the demonstrated smart grid technologies and functions. Next slide. Next slide, please. Yeah, so as we can see this table, it is build matrix calculation. The following table lists the calculated values for each of the report build matrix along with the method used to calculate them. For suppose the metric is endpoint matrix and units are endpoints, and Project contains 13,483 units and system is 231571, and the calculation is count of normal metrics from AMI head end. So like this we can study various other metrics. Next slide please. So this is in the continuation with the table. Next slide please. Yeah, benefit analysis. The SGDP operational demonstrations and testing outlined in the previous section were performed. Yeah, okay. This is repeated. The KCP&L demonstration used the DOE developed smart grid computational tool and energy storage computational tool to evaluate the overall cost and benefits of the demonstrated smart grid technologies and functions. Next slide. Smart Grid Computational Tool Analysis. Using the SGCT and SGDP team, we can identify the smart grid assets deployed, identify the smart grid functions that the demonstration would enable, and for each function, identify the applicable benefit mechanisms. Based on these inputs, the SGCT identified the expected benefits the project could achieve. The SGDP team identified several additional functions benefits not identified by the SGCT that it was able to quantify. Next slide. Yeah, so this is the SGCT function benefit chart for KCP&L and smart grid demonstration project. So here we can see there are various benefits like economic, and under economic there are various subparts, and in the right side it is smart grid functions, which is delivery, use and other miscellaneous things. Next slide. Okay, so input parameters. The SGCT uses two different types of data to calculate benefits, baseline data and project data. All benefit assumptions rely on the calculated difference between baseline and project data at a given point in time. Due to the nature of SGTP, the benefits analysis for most operational demonstration quantified most benefits as avoided cost. Using the mirror inputs capability of the SGCT, the avoided costs were entered into tools as negative value. So next slide. Yeah, so this is the tabular format of SGCT input parameters, where there is a benefit category and input name like organization name, project name, etc., and operational test which test to perform, and operational test value, then input value in 2014 and unit. Next slide. Okay, so this is results tool output. The following tables and figures provide a summary of SGCT benefits analysis for the SGDP. Table 3.164 is SGCT cumulative gross benefits summary, which is on the left side, and on the right side we have a pie chart of SGCT cumulative gross benefit summary. Next slide. Yeah, so like left table is for SGCT cumulative economic benefit summary, which where the total is $2462970, and in right side we have a pie chart uh, of SGCT cumulative economic benefit summary. Next slide. Yeah, so finally benefit summary. The SGCT benefits analysis was performed from the holistic perspective including utility, customer and social benefits. Present value benefits of $1.14 million were quantified in economics 31%, reliability 66% and environmental 3% benefits. But the overall net present value of the project remained a net cost of the utility of nearly $3. However, it must be noted that several of the SGDP systems, AMI, MDM, and some smart distribution components were capable of supporting much larger smart grid development with minimal incremental cost. For these systems, a larger deployment would result in a low cost per field unit deployed, result in a more favorable analysis. Next slide. BESS energy storage computational tool analysis. So few points are using the ESCT, the project team input the energy storage assets information, grid location, market and ownership of the BESS. Based on these inputs, the ESCT identified the expected benefits the BESS could achieve. The benefit areas quantified by the project and included in the benefit analysis are highlighted in green. And due to time constraint, we can skip some points. Next slide. Okay, so this is the tabular format of the following table and figures provide a summary of ESCT benefit analysis for the BESS, where left side is showing cumulative gross benefits over the deployment period and right side is lifetime benefit per kilowatt of energy storage installed, and the total gross benefit is $160,500. Next slide. Yeah, so this table is showing PWS ESCT benefit summary. Next slide. Okay, coming to the conclusion, the primary objectives of the KCPL Smart Grid demonstration project were twofold: to demonstrate, test, and report on the feasibility of combining, integrating, and applying existing and emerging smart grid technologies and solutions to build innovative smart grid solutions, and to demonstrate, measure, and report on the cost, benefits, and business model viability of the demonstrated solutions. Next slide. Summary: Smart Grid Demonstration Benefit Summary. Throughout the operational demonstration, KCPL identified and quantified where possible benefits resulting from deployments of smart grid technologies and implementations of specific smart grid functions. The benefits identified will be instrumental in justifying future enterprise deployment of such smart grid technologies and functions. Next slide. Yeah, so these are smart metering benefits. Some of them I will read. Like the AMI system established a daily register read performance rate of 99% and provide a more consistent performance throughout the year as compared to the legacy AMR system. On average, AMI performed 2 percentage points better than the AMR system, requiring fewer manual billing rates. So this was the first benefit, and following are the AMI infrastructure significantly outperformed the legacy AMR system for completeness of interval data, delivering 99.96% of interval usage data. And other 3 points are listed below. Next point, next slide. And other, yeah, these are the some other benefits. Next slide. Okay, so like here, yeah. Okay, so all these were the benefits of smart distribution. Next slide. Next slide. Okay, thank you. I mean, there are various benefits, and the list was too long, so due to time constraint, I have read quite a few.
Okay, okay. Even though you have taken same 1 hour time. Okay,
Yeah.
fine, fine. Good. So yeah, next batch. But still,
Thank
I
you,
didn't
sir.
receive your presentation. Did you submit?
Yes, sir, we have submitted.
Yeah,
Yes, sir.
now
Now we
it
have
is done.
submitted.
We just did it now.
Okay.
Okay, sir. Thank you, sir.
Yeah. Yeah, next batch.
We have submitted the presentation.
Yes, yes, I got
So
it.
we can, yes, sir. We'll start the presentation now.
Yeah.